Hello everyone, we are Sebastian Bock
and Leonie Schüßler from TU Darmstadt, and today we'll present our paper MUFASA, a multi-layer framework for slot attention, a joint work with Krishnakant Singh, Simone Schaub-Meyer and Stefan Roth. Object-centric learning aims to decompose visual scenes into multiple object-level representations, different from traditional deep learning approaches that encode the entire image as one global representation. A popular approach to OCL is slot attention. Here, a latent set of vectors called slots are learned in an encoder-decoder setup with a slot attention bottleneck, so that slots compete to bind to individual objects in the scene. The slot attention mask segments the scene into individual objects. Dinosaur improved upon slot attention by leveraging a pre-trained, self-supervised DinoVid as encoder, so that slots are learned in Dino's feature space rather than pixel space. Importantly though, Dinosaur uses only the output of the last layer of the encoder as input to slot attention. But what has a Dino encoder actually learned during training? Let's take a closer look. A PCA of features across layers reveals a clear representation hierarchy. Here, shallow layers contain positional information, while semantics gradually emerge in deeper layers. Especially these deeper layers encode distinct but semantically meaningful information. And, when computing slot attention on those layers, we get distinct but object-aligned segmentations. Each layer contributes different and useful information. But how can we effectively use this feature hierarchy to improve slot attention? For this, we propose MUFASA, a plug-and-play framework that can be applied to any slot attention model using a Dino encoder, while not affecting other details of the training pipeline. MUFASA extracts the representations of multiple encoder layers and introduces a multi-layer slot attention module. Here, we select a subset of multiple encoder layers and perform slot attention independently on the representation of each layer. We found the last 4 layers to yield the best segmentations. So now we have multiple sets of slots and corresponding attention masks. But how can we combine them? First, we need to ensure that across layers, corresponding slots learn to bind to the same objects to fuse them meaningfully. To achieve this, we apply Hungarian matching layer by layer, reordering the slot sets based on mean-best overlap in the attention masks. Once aligned, slots and attention masks are fused in our fusion module to obtain a single representation. For slot fusion, the sum of subsequent pairs of slot sets are concatenated along their feature dimension and then projected into a single set of slots via an MLP.
Now, does this design translate to better results? We integrate MUFASA into current slot attention methods and evaluate them on the task of unsupervised object segmentation. First, we integrate MUFASA into Dinosaur, resulting in consistent gains across 3 datasets in multiple metrics, outperforming Dinosaur by a substantial margin. When applied to the successor model Spot, MUFASA again increases its segmentation quality. This establishes a new state-of-the-art in this task across all datasets, demonstrating the benefit of leveraging multi-layer information. Let's take a look at some qualitative results to see how this corresponds to improved segmentations. In this example, both Spot and Dinosaur do not segment this very properly and merge it with the background, which is mitigated by MUFASA. Our model is also less prone to oversegmentation, as seen for the baselines in the background and on the horse's face. At the same time, MUFASA segmentations can follow the object delineations more closely. Overall, where baseline models miss object boundaries or split objects across slots, MUFASA models generate clean segmentations. To investigate how the multi-layer information manifests in MUFASA, let's examine the slot attention masks at individual layers. The mask at each layer contributes complementary information, as seen in the bench edges, which are only captured in layer 11, and also for the varying level of noise, which is compensated for in layer 10. This results in an enhanced fused segmentation. Beyond improving segmentation, MUFASA is also efficient. Our models reach baseline level performance in substantially fewer epochs, with training time reductions of up to 94%. Moreover, the multi-layer information accelerates convergence. MUFASA models reach their peak performance earlier and require less total training time. To summarize, we have seen that semantic information is not confined to the final layer of Dino, but is rather encoded in a hierarchy over multiple layers. MUFASA is a framework for slot attention that leverages this multi-layer information. Integrated into existing methods, it consistently improves our segmentation quality while also accelerating training conversions. Finally, when applied to Spot, MUFASA sets a new state-of-the-art in unsupervised object segmentation. Thank you for listening. Feel free to visit our project page for further details.